So this diagram that we worked with yesterday, I was wrong about how many there were. There's not 6, just 5. We said one of them was, and I'm going to put the names up here in case you didn't catch the names, hydroboration, oxidation, and that is a 1-2 step reaction, which is why it has 2 names. What about the second step is oxidation exactly? Hydroxide, is that an oxidizing agent? Water, is that an oxidizing agent? Hydrogen peroxide, is that an oxidizing agent? It is. Hydrogen peroxide is actually quite a reduced form of oxygen because it's bonded to itself once, so it's not fully, this is an oxidized form of oxygen, as you can see, because it's bonded to oxygen. So hydrogen peroxide will use these electrons to grab onto things less electronegative than oxygen and further reduce the oxygen, oxidizing something else in its path. Then we had oxymercuration, and depending on who you are, you might call the second step demercuration, but I have always heard that second step called reduction, and the reagent that we use for that reduction, we're going to look at again today, sodium borohydride. And I think an interesting thing about sodium borohydride is the dipole on the boron to hydrogen bond. Which of those atoms would you suspect is more electronegative? Remember that boron is just to the left of carbon on the periodic table, and hydrogen is, of course, on the top row, but who's to say whether it's left or right? Although most would suspect boron is more electronegative, hydrogen is more electronegative by 0.1 units. So the dipole here points to hydrogen, which means the electrons in those bonds are owned by hydrogen, which is why we call this reagent a hydride. We call it sodium borohydride. I'll write this down again, because hydride is essentially saying H minus. We had acid catalyzed hydration. We had diol addition. And we had halohydrin addition. And those were our 6 previously seen ways to make an alcohol. Now on this worksheet, we've got new ways to make alcohols. So we've got this long list. Could I have you guys go through and name the functional groups that you see? What do you see at number 1? Carboxylic acid. Number 2? Ester. Number 3?
Is that a carbonyl?
Carbonyl, or as I'll say, carbonyl, is not a functional group. It's a class of functional groups. It's like looking at a benzene ring and saying, is that a hydrocarbon? Yes, it is. They all are. They're all carbonyls. More specifically, Justice had it. What do you think kept you seeing those and all that?
I think just the
Yeah. Okay, actually, this is a great thing. I tell you guys over and over and over and over and over and over and over, memorize your functional groups. And the best way to do that, one of the best ways, is flashcards. This is the challenge about memorization over familiarization. If you memorize R carbonyl H, R carbonyl H, R carbonyl H, you start losing the ability to apply it into a molecule. Because I'm looking for R, I'm looking for R, I'm looking for R, and not familiarizing yourself with what R can be. R can be a CH3, R can be a benzene ring, R can be a giant molecule. How do you familiarize yourself with that? Well, you guys had an analysis assignment in the discussion boards where you had to go in and list out all your functional groups. Go look at your classmates' posts. Have you guys done that at all? Have you read through any of your classmates' discussion boards? Because you're not required to. Not an assignment, not part of the assignment, but part of the reason that I put the assignment in the discussion boards was so that you guys wouldn't have to guess molecules to go and try and apply stuff to. You could just steal the molecules that your classmates have already using. Anyways, carboxylic acid, ester, aldehyde, what's number 4? Morning.
Morning.
Evan, you want to tell us this functional group?
Some kind of carbonyl, but
Great.
I'm going to my glasses first.
Who's got this? Evan? Ooh,
That carbon's throwing me off.
interesting. This is named after the carboxylic acid. It's named as a derivative of the carboxylic acid, so it's called an acid halide, or in this case specifically an acid chloride, because that halide can also be bromine. And then the last one, the last one in the list. Anhydride, which is also named as a derivative of the acid. It's called an acid anhydride. And then what about at the very bottom, this one that's separate from all the rest? Ketone. All right, I'd like you guys to take just a few minutes before we go through the reagent that's necessary here. And I want you guys to tell me what what is that, 6? 5. What all 5 of these have in common with each other that they do not have in common with the ketone at the bottom. I'd like you to see if you could use regiochemistry descriptor terms, use your vocabulary to try and verbalize why is the ketone separated from the rest of these. And I don't want you to talk to me about it first. We've got such a small group, you don't even have to get close to each other. I'm just going to sit. Tell them.
I was gonna say, there's something other than something other than a carbon connected to that, like central carbon.
Yeah. So the degree of substitution is different.
So you're saying all of the ones on top share the same degree of substitution? All the ones on the bottom, all the ones. The one on the bottom has a separate degree of substitution. That was exactly what I was hoping you'd see. Up top, we have all primary carbonyls, if you will. Because the carbonyl carbon is bonded to only one carbon. And on the bottom, the ketone is distinct from the rest of these in that it's a secondary carbonyl. Can you apply any of that same vocabulary to the products that we see? What product is formed from the primary carbonyls? What product is formed from the secondary carbonyl?
It's the same degree of substitution as the reactant.
Can you describe the product
The top one is primary.
more? What functional group? Primary what?
Alcohol.
Okay.
Yeah.
The top one is, put it all together, Justin.
Primary alcohol,
Top one is a primary alcohol,
secondary alcohol.
secondary alcohol. Primary carbonyls form primary alcohols. Secondary carbonyls form secondary alcohols. The reactions that we are looking at on this list are considered reduction reactions. We've already reduced carbonyls. Do you remember when we took aldehydes and made alkane and ketones and made alkane during our aromatic reactions? Wolff-Kishner reduction, the hydrazine reduction, and Clemmensen reduction, the metal in acid reduction. This is less of a reduction than those. Taking a carbonyl and bringing it to strictly alkane replaces all of the bonds to oxygen with bonds to hydrogen. What we're doing here is replacing one of the bonds to oxygen with hydrogen in the case of the ketone, or for a lot of these, two of the bonds to hydrogen. Actually, the case of the aldehyde is the same. The distinction in these reductions is that it's not a complete reduction. They retain one bond to oxygen, unlike the hydrazine reduction and the Clemmensen reduction that we saw previously. These reductions were complete reductions. These are more like partial reductions. Okay, the reagents that we use, the reagent that takes any of these carbonyls and makes an alcohol, we abbreviate it as LAH. And we follow up that reaction with water or acid or just what could be referred to as an aqueous workup. So I want to talk about LAH. This stands for lithium aluminum hydride. LiAlH4, or a lithium ion balancing a tetrahedral aluminum hydride complex. Which atom is more electronegative, boron or aluminum? And I wish I had a periodic table to show you, but I will tell you they're in the same family. Boron is more electronegative. And do you remember we said boron is less electronegative than hydrogen, which means that aluminum is even less electronegative than hydrogen. So we can think of this reagent as being 4 equivalences of H minus, 4 equivalences of hydride, which is why hydride is in the name. Very strong H minuses, even stronger H minuses than from borohydride, because hydrogen owns these electrons very strongly. Okay, I will not test on these mechanisms, but I do want to show you what it looks like when hydride is acting as a reducing agent. I guess that's another thing that I want to say here. Not just a reducing agent, but a strong reducing agent. So if we take the example of our ketone, do you guys know what this ketone is, by the way, chemically? 2 methyl groups on either side of the ketone. The name of it?
What are you saying, acetone?
Acetone,
Oh.
nail polish remover.
Yeah.
I was not sure.
You didn't get my miming?
No, I wasn't sure what you were asking. That's why I was like, what?
This is acetone, CH32CO. Notice how I'm just highlighting one of those bonds between aluminum and hydrogen because only one of them is going to play a role at any given time. These electrons are owned by hydrogen and, of course, attracted to a partial positive. H minus is going to be drawn to a positive region. That's the carbonyl carbon. Can't attack the carbonyl carbon without breaking one of its bonds, so we break its pi bond. Some different ways that you might see this presented is oxygen is balanced by lithium. Some people will actually show that the oxygen complexes with aluminum. But either way, we made our alcohol, right? We now have a secondary alcohol and we're all good to go. Oh, right, alcohol needs a hydrogen connected to the oxygen. And I have an alkoxide or an aluminum oxide complex, which is why this reaction requires an aqueous workup. I don't have an alcohol right now. I'm in basic conditions, so I need to protonate my alcohol, and that's where the aqueous workup comes from. Do you guys need to see the acid-base mechanism? Oxygen takes a hydrogen from an acid source and then it's done. I labeled that as 1. I'm realizing that's how I give you guys steps of mechanisms as well. That's it. That's the mechanism's done for reduction. it's happened. I actually just wanted to give you different versions. So I think instead of 1, I'm going to call it A. The other way that we see this reducing agent actually reduce is to do acyl substitution before doing acyl addition. Okay, let's make sure that we all understand what acyl means. Acyl is referring to what? Acyl refers to the aromatic ring? No. But we did acylate our aromatic rings. We had an acylation reaction. The acylation reaction put what onto the aromatic ring? Or substituted the aromatic ring with what?
Was it in a ketone or an aldehyde?
A carbonyl. Carbonyls are acyl groups, which is why acyl addition adds across the carbonyl. Acyl substitution is going to take something off of the carbonyl and replace it with something else. So, if we take an example of the acid halide with our strong reducing agent, we'll once again see hydride attack the carbonyl and break open the pi bond. Okay, but this time, the carbon has a good leaving group. The chlorine can be broken off from the carbon rather easily. So can the anhydride, so can the ester, so can the carboxylate. So aldehydes and ketones, they go through this A mechanism. Aldehyde and ketone. All of the others, carboxylic acid, ester, acid halide, anhydride, they go through this mechanism where first it looks like acyl addition, but then the side group gets kicked off as the carbonyl reforms. See how that O minus recombines? Someone just pressed their face up against the window and I thought they were coming to say hi. I like to say that the carbonyl collapses back into itself. That negative charge from oxygen is reshared with carbon and it reforms the carbonyl. Oh, look at that. Not bad. All right, now, I'm not going to lie, I don't have the best justification for this because I don't always agree with how they might show it. So we can show how all 4 equivalences of the hydrogens from LEH are used up. I'm just going to show you guys with the strongest version of it, which is right from the beginning. So we can think of this now as byproducts. And a second equivalence now, helping to drive that second addition. I want to make a small pause when we look at A, the reduction just by acyl addition. I showed it to you on a ketone. but it could have been an aldehyde. If there had been a hydrogen on the right-hand side, in the first step, there would have been a hydrogen on the right-hand side in that second step. Hydrogen is not a good leaving group, so hydrogen wouldn't be kicked off. Aldehydes get reduced by just acyl addition. Any of our other groups, those groups that have those side chains get kicked off, and look at what I'm left with. An aldehyde. And we already know that aldehydes can be reduced by just a simple acyl addition. And so this aldehyde gets reduced further. And then, of course, we have our aqueous workup. Question. How many hydrogens were added to the carbonyl carbon when reducing the ketone? Sorry, I did forget to put my reagents up there. And just a brief change, instead of just showing H3O+, also showing water. Honestly, you could just show water. You could write aqueous workup. There are professors out there that will tell you you can assume all of your aqueous workups because they are so common and so necessary that it just becomes a little redundant, kind of like drawing all of our hydrogens all semester. So common, so redundant, we assume them. I will always push for you guys to show the aqueous workup because without it, nothing happens. You don't get your product without the aqueous workup. And if you don't recognize that you need the aqueous workup, you don't know what's going on. How many hydrogens added to the carbonyl carbon when reducing our ketone? 1 hydrogen. How many hydrogens added to the aldehyde when reducing our aldehyde? How many hydrogens added to the carbonyl carbon? 2 hydrogens added to the carbonyl carbon. It had 1 CH, now it has CH2, 1. Because aldehydes and ketones get reduced in 1 step. Aldehydes and ketones only need 1 additional hydrogen, and then they're done. How many hydrogens added to the carbonyl carbon when reducing the carboxylic acid? 2. First, 1 hydrogen is added by substitution. Then, after the aldehyde is formed, then the second one is added. How many hydrogens added to the carbonyl carbon of the ester? Carbon with no hydrogens, CH2, 2 hydrogens are added. How many hydrogens are added to the carbonyl carbon of the acid halide? 2. How many carbonyl carbons are added? How many hydrogens are added to the carbonyl carbon of the anhydride? 2. So we've got sets here. You guys see those sets? Now I want to talk to you about the byproducts. Because when the aldehyde and the ketone are reduced, there's nothing kicked off from the structure. But when all of these other functional groups are reduced, there's something else on the structure that gets substituted and then further reduced. So we're going to have byproducts for each of these. the group to the side of the carboxylic acid. In addition to making this primary alcohol, and I hope you guys see the primary alcohol, CH3 carbonyl, CH3 used to be a carbonyl. The alcohol carbon was a carbonyl carbon. CH3 carbonyl, CH3 used to be a carbonyl. Up here, we've lost the OH group, which means in addition to forming this alcohol, it kicked off a byproduct that contained that side group. After the aqueous workup, that gets protonated into water. When the ester gets reduced, it kicks off its group, which gets protonated into an alcohol. Right? Because the OR group is going to be kicked off as OR minus, and OR minus, after the aqueous workup, becomes protonated as an alcohol. So here's the fun thing I like to point out. The ester is reduced into two alcohols. The carbonyl carbon becomes an alcohol, and whatever the ester linkage is becomes an alcohol. Always two alcohols from the ester. The acid halide, we saw this, forms chloride after the aqueous workup. That's going to form hydrochloric acid. The acid anhydride, well, here's a cool thing. When the acid anhydride kicks off its side chain, it's a carbonyl, which means that even its side chain can get reduced. So in this case, the acid anhydride makes a second equivalence of the alcohol. Not just any alcohol, like the ester, but specifically the second equivalence of the carbonyl. All right. All ways for us to make alcohols. We have made alcohols by reduction. We've made primary and secondary alcohols, and that's it. We could make a methyl alcohol. Yes, sir.
The acid anhydride, what happens to the third oxygen?
Oh, well, good question. Actually, it would get kicked off much like the carboxylic acid as water. That was a great question. Okay, so Justice, what does NR mean? Did you find out?
Is it like some, like amide or?
Oh, right. That's what you had mentioned that yesterday.
Yeah.
No, it's not an amide.
Okay.
Anybody know what NR means? No reaction.
Oh, no.
Yeah, more generic. No reduction is not bad for the context, but in this case, it really just means no reaction occurs. Nothing happens. The reagent that we're going to use here instead of LaH is NaBH4 in methanol. Now, I am not entirely, I'm not entirely sure why it is this way, but I used to report these reagents as almost identical to LAH. First, sodium borohydride, then an aqueous workup. However, I'm transitioning to what I see textbooks and other resources online use more, which is that they'll report this as sodium borohydride in methanol, which actually alleviates the need to do an aqueous workup. It just feels unintuitive to me because NABH4 you should think of as a source of H-. H- is a very good base, and methanol is a good enough acid for H-. So it feels unintuitive to me that sodium borohydride can even exist in methanol. You're going to see some of my resources that still say first NABH4, then H3O+, my old resources. You're going to see some of my newer resources say NABH4 in methanol. I'll accept either one of them. Do you guys understand where I'm coming from with why it feels unintuitive? H-, source of H+, acid-base chemistry that just alleviates H2. I don't understand why methanol doesn't react with the sodium borohydride, but it is easier to write. You don't have to do the 1,2. I'll take either of these. You will see both of them. So, sodium borohydride does nothing to our carboxylic acid or to our ester. Everything stays the same with the aldehyde and the acid halide. Everything stays the same with the ketone. The acid anhydride seems to do only 1/2 of what it did. So Evan, your question earlier, where does that third oxygen go when the 2 carbonyls get reduced into 2 equivalences of alcohol? Well, actually that third oxygen gets kicked off as water because one of those groups gets transformed into a carboxylic acid, and then that carboxylic acid gets reduced. But now with this reagent, only one of the carbonyls is reduced, the other gets converted into a carboxylic acid, and carboxylic acids don't react. So in this case, we actually get two different products, one equivalence of alcohol, one equivalence of the would-be acid. Okay, so what's happening here? NABH4 is doing nothing in some of these, half of what it should in others. It's behaving fine in the rest. We call it a mild reducing agent. Could you explain to me why sodium borohydride is mild, but lithium aluminum hydride is strong?
Because the negative H's were a much stronger reducing agent than the ones in the sodium borohydride.
But they both are hydrides. They're both negatively charged H's. We can again think of this as 4 equivalences. Oh. We can think of this as 4 equivalences of H minus.
But they're stronger with the aluminum. The aluminum's less electronegative than
Perfect.
hydrogen.
Aluminum is even less electronegative than boron. So H to aluminum, big partial negative, big partial positive. H to boron, smaller partial negative, smaller partial positive. Aluminum is less electronegative than boron. So the dipole is greater between H and Al. And so H minus is more effective with aluminum. It's less effective with boron. Is this a good thing or a bad thing? I would say a good thing. It allows us to be selective when we need to be about our reagents. Like, if I have both a ketone and a carboxylic acid in my structure, I can reduce just the ketone or just the carboxylic acid, just the ketone without the carboxylic acid, or I could reduce both of them. Having the diversity in those reagents allows me to diversify what I do with my products. And the mechanism, essentially the same. Again, I don't know what methanol is doing, which is why I would encourage you to think of that methanol there as basically a replacement of the aqueous workup. Can I answer any questions about the reduction of our carbonyls here? Can I erase the board? Are you guys good? Can I erase the right-hand side? Okay. Once again, what type of alcohols have we formed so far by reduction? We have formed primary and secondary alcohols. And is that all the types of alcohols there are? What other types of alcohols are there? Tertiary alcohols. And was that it? How about the carbon that's not bonded to anything? The methyl carbon. The methyl alcohol. Unsubstituted. So let's try and make that one. I want you guys to devise 2 different reactions and use different reagents. So first, a reaction that requires LAH or utilizes LAH, maybe doesn't require. And second, a reaction that uses sodium borohydride. I want you to come up with a starting material that will give these reagents. And if you need to make anything, that's okay. You're welcome to have byproducts, which is why I'm putting plus question mark. You can have something else. You don't need to have something else. Does that make sense? But if you do make another product, then just write that one down as well. I would encourage you to work in groups on this. Brainstorm with each other. Explain to each other how you're going to get there. retrosynthesis. I like this. Reminds you of where all the hydrogens need to be and how many you can pull away. There's no one right answer, by the way, except for maybe the second one. The top one has 1,000 answers. I think the bottom one has one answer. Oh yeah, I do. Yeah, sorry.
No worries.
You're welcome. Do I need to get you into groups to make you talk? Should we just move on?
Sorry, my brain's
Maybe you can pick apart Evan's brain to get the answers from him.
I don't know.
Guess and check.
Well,
So, we need something that's just conformed. That's it's good. That's a good shooter. So, what if
I think. So what if this marker maintains the result in CH3? Because then if we do, if we use an ester, the H3O, it would give us that byproduct of CH3OH, I think.
Yeah, I was also just thinking of doing like, say, what is it called?
What's the problem with the
There's
first
just like an H on it.
the first row that we did? The ones all on the left. What's the problem with reusing those structures?
It's going to turn into a primary filial. No,
Mhm. So what's the problem?
Just for not trying
The problem about being a primary carbon. Mm-hmm. That's not enough carbons. That's too many carbons. Can you modify it to not have as many carbons?
That's what we're trying to do.
What would it look like to get rid of a carbon there?
So then would we those just be like
What would it look like if your starting material had less carbons? Do you guys remember critical versus creative thinking? This is that creative thinking side. You have to think critically, you have to know what's feasible and what's possible, but you also have to invent something new that you've maybe never seen before. Although I'm sure you have seen it. You don't know that you've seen it, so you've got to be creative about what you can see. I thought you were onto something earlier.
Almost like the ester, if that R was a CH3, would that make a byproduct?
Mm-hmm.
Okay.
Yep. Absolutely. It was.
He was saying, because I think that would work too.
Did you guys write anything?
So you take that
Can I see what you
acyl
searched?
hydride
Because sometimes the way you
instead
search
of
it.
having that carbon use an H.
Hey, not a bad idea. Maybe give it
Is
more
that what you're saying?
Yeah.
direction, narrow it in more. Because we're not just making it, I could make it a lot of different ways. But we're not making it by any specific way, we're making it by reduction with LAH. So maybe ask instead, methyl alcohol from LAH, right? Take that context. Actually, when I was tutoring in college, that's a lot of what I did. Oh, I just saw something in yours that looked exactly right. Yes, that's gonna make 2 equivalences. Right, because that's an H. Yeah, so that carbon becomes a CH3 carbon, and that carbon becomes a CH3 carbon, stays the CH3 carbon. That makes 2 equivalences. Perfect. Now, could you use the same thing here? No. Okay. Also, don't forget this is 1, 2. Did I forget that too?
What about like this poem? Is this one too as well, or just when you write it?
Just when you write it the other way. Good question.
Oh yeah.
This is not 1, 2. This is, and that's what I find is unintuitive, is that you mix it all together, but it doesn't make sense to me. But if you write it the other way, then it's 1, 2.
Oh no.
Okay, any guesses? No? Guys? So one thing that I heard from you guys was, I know that my ester will always have this leaving group from its ester linkage. So what if I just make an ester linkage that will make the alcohol I want? What if I have an ester that has OCH3? Because then that gets cleaved during the substitution part and kicks off methanol. So if I had done the same thing I did before, then I'd have another byproduct of ethanol. Or if I had done this with methyl benzoate, you guys in the lab have nitrated methyl benzoate, then the benzene ring just stays there and I get benzyl alcohol. This is that part where it doesn't really matter what else is going on with your ester, because if you get another product, you accomplished my goal still of getting methanol. But there is a way to use an ester to get 2 equivalences of methanol. What if your ester is also an aldehyde? So that this carbon, the carbonyl carbon, becomes a methyl alcohol. Not a primary alcohol, because it's not a primary carbon. Not a secondary alcohol, because it's not a secondary carbon, but a methyl alcohol, because it's a methyl carbon. This would actually make 2 equivalences of that methanol. I would have accepted either answer, because what I was looking for is how do you get the methanol to form. Just wanted you guys to find that way. Both were very clever. Once again, actually, another way you could do this, don't get the methyl alcohol from the ester linkage. but just get the methyl alcohol from the carbonyl carbon. Maybe I've got phenyl formate. And the carbonyl carbon is a methyl carbon. It's not primary, it's not secondary. It gets reduced to a methyl alcohol, and the ester linkage becomes an alcohol. In this case, it becomes phenol. Not benzyl alcohol, but phenol. So many different options, different ways to get there. And did it have to be an ester? No. It could have been that methyl carboxylic acid. It could have been that methyl acid chloride. It could have been that methyl anhydride. Ooh, by the way, in a couple of weeks, I'm going to get to nomenclature of those carbonyls, and I love it. And these are all called, they're form groups. Oh, the one I didn't show you, formaldehyde. Formaldehyde, formic anhydride, formic acid, formal chloride, methyl formate, phenyl formate. Because they're a one carbon carbonyl, they all start with form. So you could have taken formaldehyde and reduced it with LAH and gotten methanol. Actually, the opposite is what happens in your body when you drink methanol. You drink methanol and it gets oxidized to formaldehyde, and you guys know what formaldehyde is used for? Embalming bodies. It stops all life processes. Not something to be making in situ in your body. A lot of different options here. How many of these options would have worked in our second question? Only one? Which one? Is that what you said?
Yeah, the very right one.
Formaldehyde.
Yeah.
CH2O. Formaldehyde is reactive to sodium borohydride, but that's not the only one. The acid halide, formal chloride, is also reactive. I could have even gotten at least one equivalence of methanol out of my formic anhydride. But I could not use formic acid, I could not use formates, because those are inert to the sodium borohydride. They're unreactive. Great. Was that fun? Yes, it was. You're welcome. All right. We have made methyl alcohols. We have made primary alcohols, and we have made tertiary alcohols. Oh, no, sorry, secondary alcohols. But we have not yet made tertiary alcohols. And the question is, can we do that by reduction? Now, part of what I had wanted you guys to see up above was how we can take this CH3OH and reverse it take away a hydrogen from the carbon, take away a hydrogen from the oxygen, and you've got formaldehyde. That should have been the easiest one to solve, because all you had to do was remove the hydrogens that are added by reduction. And then if you recall that the aldehyde is always formed from those other carbonyls. The acid halide forms an aldehyde. The ester forms an aldehyde. The carboxylic acid forms an aldehyde. The anhydride forms an aldehyde. Then you could have taken this aldehyde and you could have substituted a hydrogen for any of those other groups. And you could have gotten to your formic acid, your methylformate, your formic anhydride, your formal chloride. Can we do the same thing with the tertiary alcohol? I can take away the hydrogen from the oxygen. Can I take away a hydrogen from the carbon? Why not?
I guess not.
It has no hydrogens. How can I take a hydrogen off of the carbon to make a precursor? How can I remove a hydrogen here such that I could have added a hydrogen to make this? There's no hydrogen. So this is impossible. There's no reduction product here. Reduction to tertiary alcohol. Well, okay, sorry. Doesn't work. I'm not exactly sure how I wanted to phrase that.
Are you saying it's because there's no hydrogens connected to that alpha carbon? Is that why?
Alpha,
Like that?
the alcohol carbon.
Yeah. So there's like no hydrogens connected to there, therefore that's why it can't be reduced, right?
Yep.
Okay. So even if you would have carbon or hydrogens connected to those other carbons surrounding that carbon, that's not necessarily possible.
Yeah, even if there's hydrogens over here on these other carbons, remember that our mechanisms showed hydrogen has to attack that carbon. But there's no hydrogen bonded to it. So what hydrogen attacked it that doesn't exist anymore? Doesn't make any sense. So I can't reduce to a tertiary alcohol, not with sodium borohydride, not with aluminum hydride, because there's no hydrogen bonded there. No hydrogens. There's no hydrogens to have added. So we introduce a new type of reagent, one that will help us get here. We introduce the organometallics. This is where you can flip your sheets. Now we're working on the back side of that same sheet. And is it obvious what I mean by abbreviating the organometallic as Rn? R is the organo, M is the metallic. So first, let's talk about how we prepare organometallics. We will start with an alkyl halide. When we react the alkyl halide with metallic magnesium, we make what is called a Grignard. Now, I don't really like the name Grignard because it doesn't tell you what it is. what I do like is calling it organomagnesium halide, because that tells you exactly what it is. Organomagnesium balanced by a halide. Now this is a reduction of the carbon because magnesium is less electronegative than the halogen. So by swapping a bond from halogen to magnesium, the carbon is gaining electrons. You will see this often drawn out as a covalent bond. That's another issue that I have with it, because I want you to think of this as a negatively charged carbon balanced by a magnesium 2+ ion balanced by a halogen ion. And there have been papers that show it has what feels like covalent character, but also what feels like ionic character. The fact that it participates in resonance on certain carbons suggests this doesn't participate in resonance. But in certain positions, it behaves as if in resonance, which suggests the lone pair is delocalized. Not localized in a sigma bond, but delocalized by molecular orbital. Okay, that's our Grignard. What charge is on magnesium here in the reagent? 0. That is metallic magnesium. Those of you in lab last week ground this up and shoved it into your reaction, and it reacts with the alkyl halide. Instead of using magnesium, we can also use 2 equivalences of lithium. And I love this. Ready? This is called an organolithium. Yeah, as it should be. It's not named after a dead French guy. Do you notice any differences between forming the Grignard and forming the organolithium? Can you point out those differences? Justice, name one of them.
One has the halide still and the other one doesn't.
Right. Organomagnesium halide versus organolithium. What else do you notice? Small things, big things? Why did I add 2 equivalences of lithium but only see 1 equivalence in the product? And not just where did the other lithium go, something else is missing. The halide's gone. Oh, does that answer the question though? Where did the halide go and where did the lithium go? Perhaps they ran away together? What charge does lithium have here in the reagent? 0. This is elemental lithium. What charge does lithium like to take on? 1+. Lithium is an alkali metal. And what charge does the carbon have here? A few other things that are different. Magnesium brings 2 valence electrons and takes on a 2+ charge. So magnesium needs to be balanced by both the carbon and the halide. Lithium brings 1 valence electron, takes on a 1+ charge. So lithium is balanced 1-to-1 with the carbon. But magnesium brings 2 valence electrons. I only need 1 equivalence. Lithium brings 1 valence electron. I need 2 equivalents. It's a 2-electron reduction, a 2-electron oxidation. The other equivalence just becomes a byproduct lithium halide salt. our third organometallic starts from the organolithium. And then we introduce copper 1 iodide. Okay, here's a, ooh, I hate this part. They will often say the organolithium is like your main equivalence. And you need 2 equivalences of organolithium to copper iodide. So we could either say 2 equivalences of organolithium to 1 equivalence of copper iodide, but because this is generally where they're starting from, they'll say 1 equivalence of organolithium to half an equivalence of copper iodide. So they'll often write this as 0.5 copper iodide. I know, I don't like it either. It looks funny. It's funny for us to use coefficients that are fractions or decimals. But that's how we get 2 equivalences of the carbon chain bonded to copper. What charge does copper have in that copper 1 iodide over the arrow? Copper, positive 1, balanced by the -1 iodide. -1 iodide, positive 1 copper. And remember, this can be thought of, oh, actually it can't. Copper is different than the others. But this should be thought of as a negatively charged carbon, negative, negative, positive 1. That's a net -1, which leaves me with a lithium balancing it. Essentially 2 equivalences of organolithium, which means I have an equivalence of lithium that is missing. I also don't see my iodide. So in this production, we make a byproduct of lithium iodide. All right, now these guys are called Gilman reagents. Although a better name for them is lithium diorganocuprates, or as I like to call them, just cuprates. And perhaps you can see that it's a little cumbersome to draw copper bonded to 2 different alkyl groups. So we will take this and we abbreviate it the way we do everything else, and we put parentheses around the group. It's important that the parenthesis goes through the bond between carbon and copper, because that's the bond that is repeated twice. It's the carbon to copper bond that is reflected in 2 different ways. I've got my butane chain. Really, it's my sec-butyl chain. And my sec-butyl chain is connected to copper twice. Oh, I'm realizing I didn't show my lithium.
Oh, yeah, that's what I was gonna ask.
Thank you. I saw you peering, wondering, and I realized what it was I missed. So our Gilman reagent can really only be made from the organolithium. But I do want to point out all three of these organometallics are so different from each other. Well, actually, they're not all so different from each other. Lithium, group 1 metal. Magnesium, group 2 metal. S block metals. They don't have electrons in their d orbitals, so they can't do d orbital chemistry. Lithium and magnesium behave pretty similar. The Grignard and the organolithium, pretty much identical. The Gilman has a copper center, and copper uses its d orbitals, so copper can do some really complex stuff that the Grignard and the organolithium cannot do. Okay, I want to point out real quick that we showed alkyl organometallics, but we can also have aryl organometallics, and we can have vinyl organometallics. A really common alkyl organometallic is inbutylene, a normal chain butyl bonded to lithium. This is a very, very strong base because carbon is a very, very strong base. But it's a very common version of the organometallic on an alkyl chain. You guys last week made phenyl Grignard. You took bromobenzene, added in magnesium, and made a Grignard, an aryl Grignard. I'm feeling like I should have given more displays of how this is made, but I feel like it's obvious. You just apply the arrow across it. Vinyl Grignard is, I want to show more than one example, but here's an alkene chain connected to my organometallic. Here's a Gilman version where there's an alkene carbon bonded directly to my copper. All of these combinations are possible. What I'm trying to say here is most of our chemistry differentiates alkyl halides from aryl halides from vinyl halides. I can't do EAS on a vinyl halide, but I can't do NAS on a vinyl halide, but I can do NAS on an aryl halide. I can do SN2 on an alkyl halide, but I can't do SN2 on these other halides. Typically, alkyl halides are differentiated by what they're bonded to, but in forming organometallics, doesn't matter. What does matter they cannot form in the presence of an acid. Just a small note to be aware of. So what's an acid? Well, when your base is carbon, everything's an acid, except for most other carbons. Alcohols are carbons. Water is a alcohol is an acid. Water is an acid. Carboxylic acids are acids. Amines are acids. So, for instance, if I wanted to take orthobromobenzoic acid. Add in some magnesium. Let's say I want to make an organometallic at that orthobromine position. You know what product you're expecting to see here. You know you're expecting to see carbon, magnesium, bromide, because that's what the Grignard is. You don't see it. You went from orthobromobenzoic acid, you tried to make a Grignard, and you ended up with benzoate. Bromine's gone. Because what you made in the middle is an aggressive carbon. It is an aggressive base. That carbon, holding that negative charge, finds a carboxylic acid nearby, deprotonates the carboxylic acid, takes its hydrogen. Not what you were probably aiming to do. So make sure that you never ever draw or try to form an organometallic in the presence of an acid. Okay, now I'm worried that you're going to think carboxylic acid is the only acid. But if this were an alcohol instead, then the only change is that you get an alkoxide instead. Because that OH is much, 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 much more acidic, and you have formed an aggressive base. And it will take a hydrogen off of anything that it can. All right, so we're going to look at the different uses of our organometallics, but I want to just wrap up today's lecture by talking about this last one. Can I make a tertiary alcohol? I saw that we did see from our alkene review that we could prepare a tertiary alcohol. Acid catalyzed hydration gave us a tertiary alcohol. But we were trying to answer, could I make a tertiary alcohol by reduction? There was no hydrogen on the tertiary alcohol that I could have added through reduction. So it just wasn't possible. But my tertiary alcohol could have had one of its R groups added on. And of course, that would mean the hydrogen on the oxygen needs to get added on at some point as well. But you might remember the oxygen got its hydrogen during the aqueous workup steps. So this hydrogen comes from the aqueous workup, and this carbon comes from the organometallic. Just like how the hydrogen came from the hydride complex, we get our carbon from the organometallics complex. Here's how I'll wrap us up today. Once again, not a mechanism I'm going to test you on, but a mechanism I have found students crave understanding to make sure that they know how to apply these reactions. And let's look at the mechanism that you guys would be doing for lab this week and last week. How do we make triphenylmethanol? I start with my phenyl Grignard. So I've got a carbon-magnesium bond. And remember, carbon is more negative, magnesium is more positive. Which means my carbon attacks my carbon. My organometallic attacks my carbonyl. Last question of the day. Is that my alcohol? Is it close to being my alcohol? What do I need to do to get my alcohol?
You need the hydrogen. So, could you do an aqueous workup?
Aqueous workup. I need to protonate my oxygen. To have a proton source, I'm going to need an acid. And so I do an aqueous workup. And I get triphenylmethanol in this case. And there's my alcohol. So, reduction, 2 steps. This is referred to as acyl addition when we use an organometallic. I showed you guys earlier the reduction is also acyl addition. We're adding across an acyl bond. But we don't call it acyl addition as often. This we refer to strictly as acyl addition. And the mechanism is almost entirely the same. It's a 1-2 step. It requires that aqueous workup. Tomorrow, we will look at I'll fill in this part of our map where we're actually doing acyl addition. But we will come back in to fill in the rest of our organometallics map. And then we're going to do some practice problems. Thank you guys for your time. See you tomorrow.